12.3 Lesson 3 Projectile Motion. Our objective for today is you'll be able to answer questions about projectile motion by analyzing the position vector for a projectile. Yesterday we looked at how we come up with this position vector for an object in projectile motion if we know the initial height, the initial speed, and the angle of elevation from which the projectile was launched. Neglecting air resistance, the path of a projectile launched from an initial height h with initial velocity v0 and angle of elevation theta is described by this vector valued function r of t. This will give you how far the object has traveled horizontally from where it was launched, and the vertical component will give you the height of the object at a particular time since it was launched. Where g is the gravitational constant, we would use 32 feet per second squared if we're measuring height in feet, and we would use 9.8 meters per second squared if we're using height in meters. So yesterday we derived this position vector starting with the acceleration vector due to the force of gravity, and then integrating that to get the velocity vector and solving for the constants of integration by using our initial conditions, and then integrating the velocity vector to get the position vector that we have here. And of course we also had to solve for the constants of integration by using our initial conditions. Yesterday we also looked at what we mean by maximum height and range, and today we're going to be using this position vector for an object in projectile motion, and using that we'll be able to answer questions about projectile motion by analyzing this model. Let's take a look at example 6. We have a baseball hit 3 feet above ground level. So that's our initial height. A baseball is hit 3 feet above ground level at 100 feet per second, so that would be the initial speed, at an angle of 45 degrees with respect to the ground. So that would be theta, our angle of elevation at launch, as shown in the figure. So if you look at the figure, this is the initial height of the ball, 3 feet above the ground. Here's the launch angle, 45 degrees with respect to the horizontal or the ground. And it is hit at a particular speed, and the ball flies off after being hit by the bat at 100 feet per second. So in this problem, we want to write a position vector for the position of the baseball with reference to our coordinate plane that I will go ahead and sketch here. So this is going to be the x-axis, and this is going to be the y-axis. So the x-axis will tell us how far the horizontal, well, if you look at the x-coordinate of the position of the baseball, it will tell us how far the ball has traveled horizontally from where it was hit. And if you look at the y component of the baseball's position, it will tell us the height of the baseball above the field at a particular time. We will go ahead and write the position vector for the baseball using theorem 12.3. We are, of course, neglecting air resistance. The path of a projectile launched from an initial height h with initial speed v0 and angle of elevation theta is described by the vector valued function r of t is equal to v0 cosine theta times ti plus h plus v0 sine theta t minus 1/2 g times t squared times the standard unit vector j, where g is the gravitational constant. And of course, since we're measuring height in feet, the value of the gravitational constant will be 32, and the units will be feet per second squared. So we'll go ahead and use all of that to write our position vector for the position of the baseball relative to the coordinate system that I sketched on the diagram. So now we have r of t is equal to v naught. Now it's important that the units for the initial speed match whatever units you're using for the height. So because the height is given in feet, we should have the initial speed given in feet per second. We already have that, so we don't need to do any conversions for this problem. So we're going to have v naught, which is 100, times cosine of theta, cosine of 45 degrees, times t, times I, plus h, which is 3 feet, plus v naught, which is 100, times sine of theta, sine of 45 degrees, times t, minus minus 1/2 times 32 times t squared multiplied by the standard unit vector j. So let's see if we can simplify that. We have r of t is equal to 100 times cosine of 45 degrees is square root of 2 over 2 ti plus 3 plus 100 times sine of 45 degrees is square root of 2 over 2 minus half of 32 is 16, so we will have this. That'll be our position vector. And of course you can simplify even further, because here you have 100 divided by 2, which would be 50. So you really have just 50 square root of 2 ti. And then here you also have 100 divided by 2, which is 50. So you have 50 square root of 2 for that term. And of course, that needs to be multiplied by t. So 50 square root of 2 t minus 16 t squared j. So that's our position vector. This tells us the position of the baseball relative to the x and the y coordinate, x and the y axes that I had drawn earlier on the diagram. Now that we have this, what would we like to do? We'd like to use our model to see if we can answer the question that is being asked in the problem. Find the maximum height reached by the baseball. And the second question is, will it clear a 10-foot high fence located 300 feet from home plate? So at some point in its motion, it will reach a maximum height, and then it will start coming back down towards the field. And we want to know what that maximum height is. So we're going to look at this analytically, but before we do that, let's see if we can graph our position vector using Desmos so we can see it graphically. So we can see where the baseball reaches a maximum height, have some idea of what that maximum height is, and then we can look graphically to see if it will clear that fence located 300 feet from home plate, and then we will do both parts of the problem analytically. So you can click on the link on the upper right corner, and that will take you to looking at this problem graphically using Desmos. So we were able to have an idea of what the maximum height would be using Desmos, that it would be about maybe a little bit more than 80 feet. And we were able to see using Desmos that it will in fact clear the 10-foot high fence located 300 feet from home plate. But now we want to do this analytically using calculus. We want to find the maximum height reached by the baseball analytically using calculus. And we would also like to answer the question of whether it will clear the 10-foot high fence located 300 feet from home plate analytically. So let's look at that. So we graphed our vector valued function for the position of the baseball relative to the xy plane as defined previously using Desmos. And the way we did that was we looked at the horizontal component and we looked at the vertical component and treated our vector valued function as a set of parametric equations. And you can see from the graph that the baseball will travel a distance of about maybe 315 feet approximately before it hits the ground. And will it clear the 10-foot high fence that's 300 feet from home plate? Here's 300 feet from home plate. This is 10 feet above the field. And you can see that the ball will clear the 10-foot high fence 300 feet from home plate. You can see that the maximum height of the ball occurs around here, and it appears that the maximum height will be a little bit more than 80 feet. So now we want to verify this analytically. So find the maximum height reached by the baseball. So how do we find the maximum height reached by the baseball? You have to look at the y component of the position vector, because that tells you the height of the baseball above the field. And you want to know what is the relative maximum of this y component of the position vector. Because what you see from the graph here is that this is a relative maximum. So how do we find a relative maximum value of a real valued function? Because remember, each component of a vector valued function is a real valued function. So the problem of finding the maximum height reached by the baseball reduces to the problem of finding a relative maximum of a real valued function, specifically the real valued function y of t is equal to 3 plus 50 times square root of 2t minus 16t squared. So we will find the relative maximum of the real valued function that gives us the y component of the position vector. That will tell us the maximum height reached by the baseball, and then we will look at the second part of the question: will it clear a 10-foot high fence located 300 feet from home plate? So how do you find a relative maximum of a real valued function? Let's review some things that we learned in Calculus AB. We begin with reviewing this concept here that you learned in Calculus AB, stated as Theorem 3.2. Relative extrema occur only at critical numbers. So to find the maximum height reached by the baseball, we will look at the real valued function for the y component of the position vector, and we want to find the relative maximum of this function. Now we know relative extrema occur only at critical numbers. So we will begin by finding critical numbers of the function y of t. What is a critical number? So once again, take a look at the definition of a critical number from Calculus AB. First of all, the function has to be defined at a critical number. And you look at the derivative of the function. If the derivative of the function is equal to 0, or if the function is not differentiable at c, then we say c is a critical number of f. So you see a couple of figures here demonstrating the two ways in which you can have a critical number of a function. Either the derivative of the function is equal to 0, in which case the critical number would represent the point on the graph where there will be a horizontal tangent line to the graph, or the critical number, you could have the critical number because the derivative does not exist. F is not differentiable at c, and you would have something like this picture. So let's go ahead and find the critical numbers of the real valued function for the y component of the position vector. So to find the critical numbers of the function, we will begin by finding the derivative and setting it equal to 0. So we're going to differentiate term by term. So the derivative of the constant term is 0. The derivative of 50 times square root of 2t is 50 times square root of 2. And the derivative of negative 16t squared is minus 32t. So now, from the definition of a critical number, first of all, our real valued function is defined for all values of t. So to find the critical numbers, we need to just set the derivative equal to 0. And since our derivative is also defined for all real values t, we don't have to worry about the other condition where the function is not differentiable. So we really just need to find the derivative and set it equal to 0 to find the critical numbers for our problem. So we set the derivative equal to 0, and we will solve for t by adding 32t to both sides of the equation. So we get t is equal to 50 times square root of 2 over 32. And you can, of course, reduce that. 2 goes into 50 25 times, and 2 goes into 32 16 times, and that would be seconds. It's approximately 2.21 seconds. So that is a critical number of our real valued function for the y component of the position vector. Now we know that relative extrema occur only at critical numbers. So if we're looking for a relative maximum, if we're going to have it, it's going to be here. So now let's look at something else that we learned in Calculus AB that would help us with this. In Calculus AB, we learned about the test for increasing and decreasing functions. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If the derivative is positive for all x in an interval ab, then the function f is increasing on that interval. If the derivative is negative on an interval, then the function is decreasing on that interval. If the derivative is 0 on an interval, then the function is constant on the interval. So let's demonstrate this theorem with the function f of x is equal to x squared. So the derivative of the function is f prime of x is equal to 2x. And if you set the derivative equal to 0 to find the critical numbers of the function, you find that x is equal to 0 is a critical number of the function. And then you can go ahead and check for the sign of the derivative for values of x that are less than the critical number and for values of x that are greater than the critical number. So we have two intervals divided by the critical number, and we're going to check for the sign of the derivative, because the sign of the derivative will tell us whether the function is increasing or decreasing on a particular interval. So on each interval, you can choose a test value. For example, -2 or +1 for the second interval. And you can evaluate the derivative at the chosen test value just to see whether it's positive or negative. So if I evaluate the derivative at x is equal to -2, 2 times -2 is -4, so the sign of the derivative is negative on the interval from -infinity to 0. And if I evaluate the derivative at x is equal to 1, 2 times 1 is 2, which is positive, so the sign of the derivative is positive on the interval from 0 to infinity. So what does that tell me? Looking at this theorem, I know that because the derivative is negative on the interval from -infinity to 0, by number 2 here, the function must be decreasing from -infinity to 0. And of course you see that. You can see that the graph is falling from left to right on the interval from -infinity to 0. And because the derivative is positive on the interval from 0 to infinity, by number 1 from the theorem, the function is increasing on the interval from 0 to infinity. And of course you can see that the graph is rising from left to right on the interval from 0 to infinity. So that's something that we learned in Calculus AB. And now we'll take a look at the first derivative test, which is also something that we learned in Calculus AB. Let's take a look at the first derivative test from Calculus AB. It says here, let C be a critical number of a function f that is continuous on an open interval I containing the critical number. If C is differentiable on the interval, except possibly at C, then f of C, the output values from the function, can be classified as follows: 1, 2, and 3. if the derivative changes from negative to positive at c, which means the function goes from decreasing to increasing at c, such as you see in this particular diagram here. The function goes from decreasing to increasing at c, then the function f must have a relative minimum at c f of c. So that's easy to understand. And look at number 2 here. If the derivative changes from positive to negative at c, meaning the function is going from increasing to decreasing at c, which means we'll have a picture like this. The graph would be rising and then falling. So that means at x is equal to c, the function must have a relative maximum. So we must have a relative maximum at c f of c. And then look at the third case. The third case states if f prime of x is positive on both sides of c or negative on both sides of c, then f of c is neither a relative minimum nor a relative maximum. And we're going to be looking at pictures that look like one of these. So you could have a critical number that is neither a relative minimum nor a relative maximum. Relative extrema occur only at critical numbers, but having a critical number by itself does not guarantee that you have a relative maximum or a relative minimum, because you could have a situation like this. And a very simple function that demonstrates this particular concept, stated as number 3 here in the first derivative test, would be f of x is equal to x cubed. You can see that with the function f of x is equal to x cubed, there is a critical number at x is equal to 0, but if you look at the sign of the derivative on the interval from negative infinity to 0 and the sign of the derivative on the interval from 0 to infinity, on both of those intervals, what is the sign of the derivative? So we're looking at the sign of the derivative on each of these intervals. The derivative is 3x squared. So whatever test value you choose from either interval, the sign of the derivative will be positive. So if the derivative is positive on both sides of the critical number or negative on both sides of the critical number, then f of c is neither a relative minimum nor a relative maximum, because the function would, in our case with our particular example, would just be increasing throughout the domain. But there will be a horizontal tangent line at the critical number, but it does not yield a relative maximum or a relative minimum. And you know that the graph of f of x is equal to x cubed looks something like this. With the concepts from Calculus AB that we just reviewed, we can now analytically find the maximum height reached by the baseball by first finding the critical numbers of the y component of the position function, and then using the first derivative test to determine if we have a relative maximum at that critical number, and whatever that relative maximum is would give us, of course, the maximum height of the baseball. And then we will move on to the second part of the question and how to do it analytically. Will it clear a 10-foot high fence located 300 feet from home plate? So earlier we found that t is equal to 25 times square root of 2 over 16, or about 2.21 seconds, is a critical number of the y component of the position function. So now we will check for the sign of the derivative of y on the time interval preceding the critical number and the time interval following the critical number. So when we do that, here's what we will have. We will have our number line representing times, and here's our critical number, 25 square root of 2 over 16. And in this problem, we will actually start at time is equal to 0, because that makes sense for our problem. And realistically, the time interval will not go on forever. it'll actually stop at a particular value when the baseball lands and hits the ground. But we can go ahead and choose, for example, time is equal to 2. We can also choose, for example, time is equal to maybe 2.5 seconds. And then you can check for the sign of the derivative at each of those test values. So at the test value of 2, you will find that the derivative is positive, which means the function y of t is increasing on the time interval from 0 to about 2.21 seconds, which means the heights are increasing. And then if you check for the sign of the derivative at time is equal to 2.5, you will see that the derivative is negative, which means on the time interval after the critical number, the function y will be decreasing, which means the ball will be falling, which means by the first derivative test, at the critical number, we must have a relative maximum of y of t. In other words, at the critical time, we must have a maximum height of the baseball by the first derivative test. So the next thing that we must do is to find what the maximum height is. Now that we know that the baseball will reach a maximum height at this particular time, we need to find what that maximum height is. And to do that, we will simply evaluate the real valued function that gives us the height of the ball at time t at this particular time, and that will give us the maximum height of the baseball. So we will have y evaluated at 25 square root of 2 over 16, or approximately 2.21 seconds. And if you do that, you will get that this is 649 over 8, and that is approximately 81 feet. And that would be the maximum height of the baseball. And it is, as you can see, consistent with the graph that we had from Desmos. The maximum height does appear to be a little bit more than 80 feet. So now we have answered that question, and we will now look at the second part of the question. Will it clear? Will the baseball clear a 10-foot high fence located 300 feet from home plate? How will we do that? To answer the second part of the question analytically, we've got to read the problem carefully. Will it clear a 10-foot high fence located 300 feet from home plate? And when you look at the position vector, the x component tells you the distance the baseball is from home plate at time t, and the y component tells you the height of the baseball above the field at time t. So to answer the question, will the baseball clear a 10-foot high fence located 300 feet from home plate, we're really asking when the baseball has traveled 300 feet from home plate, what would be its height above the field? We want to know when the baseball has traveled 300 feet from home plate, what will be the height of the ball above the field at that time. So the horizontal distance from the home plate would be 300 feet, but the question is, what will be the height of the ball above the field at that time? And specifically, will it be more than 10 feet so that it will clear the fence? So to do that, we just simply take the horizontal component of the velocity vector, and we have to set that equal to 300 to find the time at which the ball would have traveled a horizontal distance of 300 feet from home plate. And then once we have that time, we will evaluate the vertical component of the position vector at that time and see if that height is more than 10 feet. So we begin by setting the horizontal component of the position vector equal to 300, and we will solve for the time by dividing both sides of the equation by 50 times square root of 2. And when you do that, 300 divided by 50 is 6. So you get 6 over the square root of 2. You can rationalize the denominator and you'll get 6 times the square root of 2 over 2, or 3 times the square root of 2 seconds. That is approximately 4.24 seconds. So 4.24 seconds after the baseball was hit, it would have traveled a horizontal distance of 300 feet. What is the height of the ball at that time? And specifically, we want to know, is the height of the ball more than 10 feet at that time? So what we do is we're going to look at the vertical component of the position vector, and we will evaluate the vertical component of the position vector at this time and see what the height of the baseball is at that time. So we have y of 3 times the square root of 2 For many problems, you'll just use the decimal approximation. Try not to round too much so that you don't affect the accuracy of your answer. But in this particular problem, you can actually use the exact value of the time. So what you get is 15 feet. And you will see that 15 is more than 10, so the baseball will clear the fence after it has traveled a horizontal distance of 300 feet, because the fence is only 10 feet high, but the height of the baseball at the time it reaches the fence is 5 feet higher than the top of the fence, so it will easily clear the fence. And you will have a home run. So today we were able to answer questions about projectile motion by analyzing the position vector for a projectile. And in our lesson today, we also took the opportunity to review some concepts from Calculus AB about critical numbers, and relative extrema occur only at critical numbers, how to test for increasing and decreasing functions, and the first derivative test for relative extrema.